So hi everyone. I am Neelav Bhatiya. I've just completed my third year in computer science and engineering from NIT Surat. I gave my JEE in 2020, and at that time I secured an AIR of 1755 in JEE mains and 5693 in JEE advanced, right? And in the previous session I had started with trigonometric functions, and we had completed two exercises regarding that. Today, we'll try and see the exercises that are left and we'll try and go over them. Before I start today's session, some key points that I would like everyone who's watching this video to keep in mind is that if you do not actually remember the identities and various other equations that trigonometry uses, so first, before attempting this exercises or seeing this video, I would like you all to kind of go through them, because when you have seen these identities, when you have memorized them, it's very easy for you to solve questions, right? So you should not start attempting the exercise just like that. First, make a list of all the equations, all the identities that you encounter, and kind of try and remember them, right? I would recommend that in this particular in this particular chapter, you make a cheat sheet of a kind, right? To write down all the things you understand in the chapter, right? So uh, I would now present my screen. Yeah, so I hope everyone's able to see the screen that I'm currently presenting. And yeah, okay. So I guess everyone's able to see that. So without wasting any more time, we'll jump into today's exercise, right? That we have to solve. So the first exercise that we are looking at today is in exercise 3.3, we're going to start with the first question, right? The first question is prove that sine square pi by 6 plus cos square pi by 3 minus tan square pi by 4 equals minus 1 by 2. Correct. So this is something that we have to prove. So looking at this question, this is a very basic question. All we need to do is we will solve for LHS, right? We'll plug in all the values that we can see here on the left hand side. And when we do that, we'll try and see if we get the term that is on the RHS. Correct. So let's do that. I'll solve for LHS. Correct. So what is sine pi by 6? Pi by 6 is nothing but 180 degrees divided by 6. Correct. Because we denote pi radians as being equivalent to 180 degrees. Correct. So that is nothing but 180 divided by 6, and that is 30 degrees. And what is the value of sine 30? It's nothing but 1 by 2. Correct. So 1 by 2 whole square plus now cos pi by 3, right? So pi by 3 is 180 by 3, the same formula that I'm using, right? That will be 60 degrees. And we all know the value of cos 60 degrees. That's also 1 by 2. So I'll write 1 by 2 ka square once again. And then for pi by 4, 180 divided by 4, that's equivalent to 45 degrees. And we know that tan assumes the value of 1 when the degree measure is 45 degrees, correct? So we subtract 1's whole square, correct? That is equivalent to 1 by 4 plus 1 by 4 minus 1. So you can add these terms up. This equals to half minus 1. That is minus 1 by, correct? So this term right here is our RHS. And we have solved that, correct? So this is the first question, exercise 3.3. Now moving on to the next question, correct? So the second question asks us to prove 2 sine square pi by 6 plus cosec square 7 pi by 6 cos square pi by 3 equals 3 over 2. Correct. So the approach that we used in the last question was that we tried to solve LHS and equate that to RHS. We are going to use the same approach in this question as well. So I'll start solving for LHS and let's see if we can come to the RHS, right? So 2 times sine square pi by 6. So pi by 6, as we know, as we have solved before, is that is 30 degrees, correct? So sine square 30 degrees, or rather than writing that, I'll just plug in the value of sine 30. Right. So sine 30 is 1 by 2. Correct. We saw that. So I'll write 1 by 2's whole square. Correct. I'm doing nothing except writing what is written in the LHS and plugging the values here. Correct. Now for cosec square 7 pi by 6. Okay. This is going to be interesting here. So what do we know about cosec? What is the time period of cosec? Right. That is something that we need to do. Try and understand that. When I write cosec 7 pi by 6, isn't it equivalent to writing cosec pi plus pi by 6? Take a minute and understand this, right? We can denote 7 pi by 6 in this function along these lines. And this will be the third quadrant, correct? So can't I write this as cosec minus cosec pi by 6, right? And we all know the value of cosec pi by 6 or cosec 30 degrees, and that's just 2. So I get cosec 7 pi by 6 as minus, correct? So now I'll plug in the value of cosec from here into the equation above, and the value of cos pi by 3, that is cos 60 degrees, is 1 over 2, correct? I'll plug in that value as well. So let us try and solve this. So I get 2 into 1 over 4 because of half square right here. The negative sign gets removed. I get 4 into 1 over 4, correct? 4 and 4 gets cancelled. This gets cancelled, and this is what remains. Now I get 1 plus 1 half plus 1. That comes out to be 3 over. And this term right here is equal to RHS. Hence, correct. We'll now move on to the third question. Prove that cot square pi by 6 plus cosec pi by 6 plus 3 tan square pi by 6 equals to 6. You have to prove this, correct? So let's try and do this. What is cot pi by 6? Pi by 6 is nothing but 30 degrees, right? And we all know the value of cot 30. That is root 3, correct? So I'll plug in the value of root 3 right here. Now, what is cosec pi by 6? So as I was saying, we can write cosec pi by 6 as cosec pi minus pi by 6, correct? And we all know that this is in the second quadrant. In the second quadrant, cosec and sine are positive. So what we get is cosec plus pi by 6. And cosec pi by 6 is nothing but 2, correct? So I'll write 2 here. Moving on, 3 into tan square pi by 6. We know that tan pi by 6 is 1 over root 3. Plug this value into the equation. When you do that, square this 3 plus 2 plus 1, that comes to be 6, correct? And that is the RHS as well. So this is also proved, correct? Let's move. Prove that 2 sine square 3 pi by 4 plus 2 cos square pi by 4 plus 2 sec square pi by 6 equals to 10, correct? So this is something that we have to prove. We'll start again with the same approach. We'll start from LHS and we'll try to prove the term on the RHS, right? So sine 3 pi by 4. Sine 3 pi by 4 can be expressed as sine pi minus pi by 4, and sine is positive in the second quadrant. So that is nothing but sine pi by 4, correct? So I'll plug in the value of sine pi by 4, that is sine 45 degrees, into the equation. I get a whole square, correct? Now let's go on. 2 times cos square pi by 4, correct? So that is nothing but 2 times 1 over root 2 ka whole square, correct, plus 2. And what is sec pi by 3? Sec pi by 3 is nothing but inverse of cos pi by 3. Cos pi by 3 is half. So sec pi by 3 would be 2, correct? This 2 and this 2 gets cancelled. This 2 and this 2 gets cancelled. I get 1 plus 1 plus 2 into 2, correct? This term, entire term is 8. Here I have 2 more. That comes to be 10. It's equal to my RHS cut term. Correct. So this is also proved. The fifth question is actually a two-parter. And from the fifth question onwards, we are going to see a pattern of applying identities across, right? We are now going to see how we apply, like how do we solve questions of the format that has two degree terms inside the sine function. Like let us suppose I want to express sine x plus y. So I would need to know the expansion for it, right? So the questions of those type have begun now, and they'll carry on for the rest of the exercise, right? So I'll write the fifth question. Yes, I'll write the first part of the first question, that is sine 75 degrees, right? So at first glance, this does not seem to be of any general degree term that we know, right? We know the values of 30 degrees, sine 30 degrees, we know the value of sine 45 degrees as well. We know the value of sine 60 degrees, we know the value of sine 90 degrees, and so on and so forth, right? But sine 75 degrees is something that we don't learn. So here, a very important identity is applied, right? We express, or we kind of break down 75 degrees as being equal to 30 plus 45 degrees. This was the main catch in the question. And as we all know, sine x plus y is nothing but sine x cos y plus cos x sine y. Correct? Now try and plug in these values here. You get sine 30 degrees cos 45 degrees plus cos 30 degrees sine 45 degrees. Correct? Plug in the values of all the cos function and sine functions here, right? Sine 30 degrees is nothing but half into cos 45 is nothing but 1 over root 2 plus cos 30 degrees is nothing but root 3 over 2 into sine 45 degrees is nothing but this, right? So at the end, the term that you get is root 3 plus 1 over 2 root 2. Correct? So that is our ultimate answer. Correct? I hope this was clear. So as you can see, this particular identity was used here. And as I told you in the beginning itself, these questions are going to be easier for you if you remember all these identities. There are like in the NCERT itself, I've seen about 20 odd identities. If you remember them all, that will be all right. For this chapter, if you remember 20-25 odd identities, then you'll be able to solve most of these questions, right? Move on to the next part. Question 5, part 2. And 5 part 2 tells us to find the value of tan 15 degrees. And as was the case in the first question also, we are not able to see any particular set of values which we remember, right? 30 degrees, 45 degrees, 60 degrees. That's not in that range. So I'll try and break this 15 degrees into something of the form that we are able to plug in values and so on, right? Can I write tan 15 degrees as being equal to tan 45 minus 30? I can write this, right? And when I have equation in this format, I know what is, I need to know the expansion of 10x minus y. So if you open an NCERT, you can look around, you'll even find derivations for this. For the sake of time, we won't go into the derivation of tan x minus y, but that is just equal to tan x minus tan y 1 plus tan x and y. Correct? Forgive my handwriting. And now when I plug in these values here, I get 45, 30, 1 plus 45 30. Correct. Solving this further, I get 1 minus 1 plus 1 over 3. Correct. So I have 1 upon 1 minus root 3 upon 1 plus 1 over root 3. Correct. Now I can take common fractions and I can eliminate this root 3, right? What I'll do is I'll multiply both the denominator and the numerator by root 3 and I'll try and see what I get, right? So just do that, multiply on both the sides, right? You'll get root 3 minus 1 upon root 3 plus 1. Correct. And now this is the answer right here, right? But if you want, you can rationalize this as well. I'm going to rationalize this once, and for the other times you can do it by yourself, right? So I'll try and rationalize this. To rationalize this, multiply this by its conjugate, that is root 3 minus 1. Do that on both the sides, both the numerator and the denominator. So this right here, it's rub this, I'll solve this here. This goes here. We get root 3 minus 1's whole square upon root 3 square minus 1. Correct. So I get 3 plus 1 minus 2 root 3 upon 3 minus 1. I get 2 minus 2 root 3. 2, that is nothing but 1. Sorry, I've done something wrong here. That is 4, not 2. That will be 2 minus root 3. So 2 minus root 3 is my final answer and the question is solved. Correct. Now let us try and move on. Now question number 6. Correct. Question number 6 is a very interesting question. And now the calculative part of the exercise is mostly done, right? Now all we need to do is we need to apply identities and try and resolve and try and prove what is given to us, right? So here begins the interesting part, right? Question number 6, prove that cos pi by 4 minus x cos pi by 4 minus y sine pi by 4 minus x sine pi by 4 minus y equals to sine x plus y. Correct. So this is something that we have to prove. Correct. At a glance, this question might seem very daunting. It looks very challenging, right? But try and kind of visualize it in a different way. Do one thing. Understand this entire term as A and understand this entire term as B. Correct. Let us try and see if we can find any patterns after writing this in this format, right? Cos A cos B minus sine A sine B. Can you see something? Isn't this the format for writing cos A plus B? Does that make any sense? So if we write cos, if we consider this terminology to represent this entire equation, it boils down to just cos A plus B. Correct. I hope you guys understood that, because this is also A, right? This is also B. Does that make sense? So now I'll rewrite the LHS term and let us see if we get somewhere. Right. So using the identity that I stated above, cos, we're going to use this identity cos A cos B minus sine A sine B equals to cos A plus B. So remember this identity we're going to use here. Consider this as A and this as B, and let us write LHS, right? So using this identity, I'm able to express this as pi by 4 minus x plus pi by 4 minus y. I hope this was clear. I've represented this term as a and this term as b, and I've just taken their addition, right? And this is nothing but cos pi by 2 minus x plus y, correct? So what is cos pi by 2 minus anything? That is nothing but sine that term, right? If we write cos pi by 2 minus x, isn't it this a way of writing sine x, right? So I'll use that identity here as well, and ultimately I am going to get sine x plus pi. That is nothing but my RHS, correct? So it is all about visualizing. It is all about using those identities that you have learned in the chapter and trying and finding out patterns in between the question. If you are able to see how to express terms, you'll be able to solve it pretty easily, right? Moving on. Question number 7, correct? Prove that tan pi by 4 plus x upon tan pi by 4 minus x equals to upon 1 plus tan. Yeah, correct, right? This is something that you have to prove. Let us start with the LHS as always, right? So seeing this term, what identity do you think applies here? Don't you think the identity tan x plus y written as tan x plus tan y 1 minus tan x tan y applies here? It does, right? So let us try and express these both the terms as being subtraction and addition inside the tan function, correct? And we know the identities for that as well. So we are going to apply these two identities, and tan x minus y, that is used in the denominator, could be expressed as tan x minus tan y 1 minus 1 plus tan x tan y, correct? And yeah, so use this here and use this here, correct? And what do you get after that? I'm going to write it here. X is pi by 4, so 1 plus tan x upon 1 into 1 tan x, correct? And the denominator I'll have 1 minus tan x on 1 plus tan x, correct? Now invert it into the numerator, correct? This multiplies here and this multiplies here, correct? So at the end what you'll have is 1 plus tan x whole square. Sorry for the disturbance, guys. 1 minus tan x whole square, correct? And this is nothing but my RHS term, correct? So this is solved here. Let us move on to the next question. Question number 8 asks us to prove cos pi plus x into cos minus x upon sine pi minus x cos pi by 2 plus x is equals to cot square x. This is what is asked of us in question number 7, correct? Now this entire question comes out to be easily solved when you know when cos, what are the signs of cos, sine, cosec, sec, tan and cot in all the quadrants, correct? If you remember the sine functions very well, then you will be able to solve this pretty easily. So let's try and do that, right? Let's try and simplify LHS. Cos pi plus x. So cos pi plus x, if we see, if I'll make a quadrant here, pi somewhere here, and pi plus x would be somewhere here. It will be in the third quadrant. Is cos positive or negative in the third quadrant? It's negative, right? So I can write this as minus cos x. The sign of cos won't change because we are taking with reference to pi, correct? So it will be minus cos x. Correct? Cos minus x. So cos minus x is nothing but the mirror image of cos across the zero line, right? And we know that cos minus x is just equal to cos x. So I'll write cos x here. Sin pi minus x. This is the pi line. So sin pi minus x would be somewhere here. Correct? If you consider this x, sign would be positive. Correct? So I'll just write sin x. Correct? And cos pi by 2 plus x would be in the second quadrant. In the second quadrant, cos is negative. But I am taking with the reference to pi by 2. So that will change to sine. So it will ultimately become minus sine pi by, minus sine x. Correct? Negative and negative sign gets cancelled. What you're left with is cos square x upon sine square x, and that is nothing but cos x upon sine x's whole square. It's nothing but cot square x. Correct? And this is the RHS. We solved this. Correct? You could have applied identities here as well. You could have expanded this pi plus x, this pi minus x, pi by 2 plus x, but that would have been a very lengthy procedure. If you remember, if you can draw this circle, right, and kind of figure out where the angles are going to be at, you'll be able to figure out the signs as well, and then you can solve this. Correct? Moving on to question number 8. Correct? Cos pi. Yes, we solved question number 8. Sorry. Solve that, right? Sorry. We solved question number 8. We go on to question number 9. Right? So question number 9 is nothing but we have to prove again cos 3 pi by 2 plus x cos 2 pi plus x to the bracket 3 pi by 2 minus x plus cot 2 pi plus x. Correct? This is something that we are asked to solve. Correct? So we're going to employ the same procedure again. We're going to figure out what various angles are going to be at. We are going to draw a circle here, and this is equal to 1. That is something that we have asked to prove. Right? We are going to draw a circle here. Whenever you see questions of this accord, don't try and expand this. Right? That will be very lengthy. If you expand this, you have to expand this as well. You have to expand this and this. They'll be very lengthy. Just draw this circle. Right? That will represent the 4 quadrants, and you'll be able to figure out what each term is going to be, right? So I'll try and do that. Let us try and simplify the LHS term. Correct? Cos 3 pi by 2 plus x. So 3 pi by 2 is somewhere here, and we add x to that. So we are here in the 4th quadrant. In the 4th quadrant, cos is going to be positive. So we know the sign of this term, this first term, is going to be positive, but the function is going to change because the reference lines is often multiple pi by 2. So I can write this as sin x. Correct? Cos 2 pi plus x is nothing but with reference to this, and that is nothing but saying it is located in the 1st quadrant. Because the reference line is a multiple of pi, we won't change the cos function. It will remain cos, and as it is in the 1st quadrant, the sign also is going to be positive. Correct? So just cos x. Right? Cot 3 pi by 2 minus x. Now this is going to be interesting. Let's try and see what this comes out to be. So cot 3 pi by 2. So 3 pi by 2 is here. Minus x, so in the 3rd quadrant, so it's going to be positive. First of all, I know that for a fact because cot and tan are positive in the 3rd quadrant and in the 1st quadrant. So this term is going to be positive. But because the reference line is a multiple of pi by 2, the function is going to change. It's going to become 10x. Does that make sense? Yeah, correct. And this term right here, cot 2 pi plus x, is nothing but saying that it is located in the first quadrant, because the reference line is a multiple of pi. We won't change the function as well, just remain cot x, correct? So I have reduced this entire term without expanding, mind you, into this simple formation. Now you can write tan as being sin x over cos x and cot x as being cos x over sin x, correct? When you multiply this term inside both the terms, you'll get the sine, the cos and cos gets cancelled in the first term, you'll get sine square x plus the sine and sine gets cancelled in the second term, we'll get cos square x. And we all know sine square x plus cos square x equals to 1. Question is solved, correct? Because that is the RHS. Moving on to the next question. Question number 10. So at a first glance, this question might seem a bit complicated, right? Because it has various terms here, right? It has n plus 1 that is multiplied by x. It is n plus 2 that is multiplied by x. But the question becomes very simple when you try and identify the pattern here. Cos term is multiplied into cos term, and that is added to two sine terms that are multiplied, right? Whenever you see questions of this accord, the identity cos A minus B equal to cos A cos B plus sine A sine B should strike, correct? Do this, apply this identity in this question, and let us see what we get. This is our A, this is our B, correct? So can I write this as cos n plus 2x minus n plus 1x? Can I write this? I can, right? Because this is also A, B, and this is also A, correct? I have just used this identity above and I have written this in the simplified form, right? This is the LHS, by the way. When I do this, let us try and multiply x inside, get nx minus nx plus 2x minus x. X and x gets cancelled, and I'm left with cos x, correct? And that is equal to RHS as well. The question is solved. Number 11. This is the 11th question, right? We have to prove this. So again, we are going to use the same approach. We are going to expand everything in the LHS, and we're going to try and get our RHS, correct? So first, to expand this term, you need the identity cos A plus B. We all know what is cos A plus B. Cos A plus B is nothing but cos A cos B minus sin A sin B, correct? I'll write that. Cos 3 pi by 4 cos x minus sin 3 pi by 4 sin x. Before plugging these values, I'll try and expand this as well and see if something is getting cancelled, right? Into the negative sign. I'll expand this term as well. Cos A minus B. Now cos A minus B is nothing but cos A cos B minus plus sin A sin B. I write that again. Cos 3 pi by 4 cos x plus sin 3 pi by 4 x. It's very easy to see that this term and this term gets cancelled, correct? The negative changes the sign inside here, right here. And what we get is 2 sin 3 pi by 4 sin x, correct? And 2 into sin 3 pi by 4 is nothing but into 1 over root 2 sin x, correct? This 2 is cancelled. I've plugged in the value of sin 3 pi by 4 into the equation, and we know that sin 3 pi by 4 is nothing but sin is equal to sin pi by 4 as well, right? Because we can expand 3 pi by 4 as being equal to pi minus pi by 4, and that is in the second quadrant, right? So you get minus 2 sine x minus root 2 sine x, and that is the RHS as well. Our question is solved. Correct. In the 12th question, we have to prove 6x sine square 4x equals to x. Correct. And let's try and write this, right? Can we write sine 6x minus sine square 6x minus sine square 4x as being equal to sine 6x plus sine 4x, and that term into 4x. Correct. What is going to happen when you're going to try and expand these two terms? What will happen? But rather than doing this, aren't we aware about a different identity? Like, aren't we aware about an identity that we've probably learned in an NCERT about something along these lines? Sine square A minus sine square B equals sine A plus B, A minus B. Correct. Are you aware about this identity? This identity is used in NCERT textbook. Just try and find this out. And when you apply this identity, it's a very straightforward question, right? Just boils down to sine 6x plus 4x. I'm just solving, plugging the value of 6x and 4x from the equation up above. Sine 6x minus 4x. Correct. I'm just plugging the values into the equation that I found, right? I get 10x sine 2x. Correct. And the question is solved. Just a moment, I need to find my charger. Comes. Moment, guys. Charger back on track. Yeah, this question is solved. This is a very important entity because whenever we try and reduce the question up until this form, you can directly apply this entity and we can get the answer, right? So this is something that you guys should remember. I'll move on to the next question. Number 13. Question number 13 states that we need to prove cos square 2x minus cos square 6x equals to sine 4x 8x. Correct. This is something that we have to prove. Now, try and understand this. We have an identity along the lines sine square A minus sine square B equals sine A plus B sine A minus B, right? This is the identity that we have. But we don't have a matching identity for cos. So isn't it convenient for me to reduce the cos and I'll try and express LHS along some different lines. I'll express LHS as 1 minus sine square 2x. This cos square 2x becomes this minus 1 minus sine square 6x. Correct. I can do that, right? I have just replaced the cos square 2x and cos square 6x as these two terms. You'll get 2x 6x. Correct. This is correct. Now we have reduced this to a term where this identity can be applied. Correct. You got how you understood how I got here, right? I've applied the minus sign into the brackets and I've gotten here. And after this, we can directly apply this identity and we can finally get 6x plus 2x sine 6x minus 2x. Correct. That is nothing but sine 8x sine 4x. That is my RHS. Question is solved. Correct. Moving on. Yeah. So the next question is question number. The next question is question number 14. Correct. Let us try and see what we have here. Sine 2x plus 2 sine 4x sine 6x equals to 4 cos square x sine 4x. Right. This is inside a multiplication term. Sine 4x. Right. So whenever we see questions of this accord, something very trivial should strike our mind. Right. Can we somehow find 4x this term? Because we have 4x right here. But if you see properly, when you add sine 6x plus sine 2x and apply the identity that we know that sine 6x sine x plus sine y equal to 2 times sine x plus y by 2 into cos x minus y by 2, correct? And apply that identity here. Very wonderful thing comes out of that, right? You can get 4x common, sine 4x, this term common. When you add these two terms up and apply the identity, this identity you can apply, the 4x term, it's common, right? Let's try and do that. We get 6x plus 2x divided by 2 cos, plus 2x cos 6x plus 2x divided by 2 plus 2 sine 4x. Correct. And when I do this, I get 2 times sine 4x cos 2x plus 2 sine 4x. Correct. Now, the interesting part comes. I'll take this and this common, right? So I'll get 2 times sine 4x 1 plus cos 2x. Correct. Now the interesting part comes. Do we know that we can write cos 2x as cos square x? We can write this term right here as 2 cos square x minus 1. Do you get how we got here? We could do that because this term right here could be written as cos x plus x, and cos x plus x, when you expand that, you'll get cos x into cos x minus sin x into sin x. Correct. And further simplify this as cos square x minus sin square x, and sin square x could be written as 1 minus cos square x. That is how cos 2x would ultimately be written as 2 times cos square x minus 1. Makes sense? But this is something that you should remember. So 1 plus cos 2x, you can directly write down as 2 times cos square x. Right? Try and plug in those values right here and see what we get. So this equals 2 times sine 4x, 1 plus 2 cos square x minus 1. 1 and 1 gets cancelled. 2 gets multiplied. What you're left with is 4 times cos square x sine 4x. That is nothing but our RHS as well. So we have solved this question, right? These types of expansion, right? 1 plus cos 2x is equals to 2 times cos square x. 1 minus cos 2x equals to 2 times sine square x. These kind of things, you should just memorize them, right? So whenever you encounter this particular term, you can directly substitute this as 2 cos square x. So this is something that you, this knowledge that you gain, you solve too many questions, and you should try and inculcate into practice, right? Moving on, we move on to the 15th question. Right. So this question is kind of in a different format. If you just start from the LHS and try to reach the RHS just by itself, it's going to get a bit difficult for you, right? It's going to get difficult. So what is something that you can do here is you can reduce this to a certain form and try and see if you can bring the LHS and RHS to common form. So try and solve both these sides simultaneously. That is how you're going to arrive at the solution, right? Because if you just start from the LHS and try to reach RHS just by itself, it's going to get very tedious for you. So what I'm going to do is I'm going to reduce LHS to a certain form, and then at that form, I'll try to bring RHS as well. And that is how I'm going to solve this question, right? So first I'll solve LHS, right? So cot 4x, let us keep it as it is, into sine 5x plus sine 3x. What is sine x plus sine y? It is nothing but 2 times sine 5x plus 3x by 2 into cos 5x minus 3x, correct? And when you solve this, you get 4x, 2 comes out here, sine 4x into cos x, correct? Now there is nothing but just write this as cos 4x sine 4x. I'm just writing cot 4x as expressed into cos and sine terms into sine 4x into cos x. Sine 4x and sine 4x gets cancelled, and we get 2 times cos 4x into cos x. Now at this particular point, just try and stop. Just try and stop here. Let us try and bring RHS as well as being equal to 2 times cos 4x cos x. And if we can do that, our question is solved there, right? So I'll try and solve RHS. Cot x. Now we know the formula for sine x minus sine y. That is nothing but 2 times cos x plus y by 2 into sine x minus y by 2, correct? So I'm just going to write that into 2 cos 5x plus 3x by 2 sine 5x minus 3x by 2, correct? That is nothing but I'm just taking 2 outside, and I might as well write cot as being equal to this. This is nothing but cos 4x. So I should not write it because I've written this here as well. And this is just sine x, correct? So sine x and sine x gets cancelled, and what you are left with is 2 cos 4x cos x. And this is the same term that we got in the LHS as well. Because these two terms are equal, our question is proved, correct? So if you had rather tried to just derive RHS from LHS only, you would have been stuck here, right? You would have to apply more and more entities here to ultimately get to here. So rather than doing that, just try to make both LHS and RHS equal to one common form. That is how you're going to solve questions of these type, right? Moving on. A 16th question. We have cos 9x 5x 17x 3x. So this is something that you have to prove. Let's start from the LHS and try and see that if we can reach the RHS, right? So first of all, cos 9x minus cos 5x. Now this could be expressed using the identity cos x minus cos y, and that is nothing but 2 times sine x plus y by 2 into sine y minus x by 2. Or you can take the negative sign outside, you can just write x minus y, but don't forget to mention the negative sign outside then, right? So I'll try and write that. Put the negative sign first outside, right? Sine 9x plus 5x by 2 sine 9x minus 5x by 2. Correct. And here there is sine terms, right? So all I need to do is cos. We all know that sine x minus sine y can be written as 2 times cos x plus y by 2 into sine x minus y by 2. That's what I'm going to do. 17x plus 3x by 2 into sine 17x minus 3x. Correct. This 2 and this 2 gets cancelled. 9 plus 5 is equal to 14 divided by 2 is 7. So sine minus sine 7x into sine 2x, because 9 minus 5 is 4 divided by 2 is 2. And here I have cos 17 plus 3 is 10. 17 plus 3 is 20 divided by 2 is 10. I have cos 10x. 17 minus 3 is 14 divided by 2 is 7. So I have sine 7x. Sine 7x and sine 7x gets cancelled. I'm left with sine 2x, negative of that, divided by cos 10x. That is my answer. Correct. So let's try and move on. Next question. The next question is also of the same accord. The questions, the patterns of the questions are repeating now. We just have to apply the same formula of sine x plus sine y or cos x plus cos y, or putting the negative sign there. Let us try and solve the 17th one. The 17th one, we have to prove that sine 5x plus sine 3x divided by cos 5x plus cos 3x equals to tan 4x. Correct. So this is going to be very simple. We're just going to solve for LHS and then we are going to get RHS. Apply the identity sine x plus sine y, that is equal to nothing but sine 2 times sine x plus y by 2 cos x minus y, cos x minus y by 2. Correct. So cos x minus x by 2. Correct. And in the denominator, what do we have? What is the formula for cos x plus y? Cos x plus y is nothing but 2 times cos x plus y by 2 into cos x minus y by 2. So I'll just write that cos 5x plus 3x by 2 cos 5x minus 3x. We don't even need to solve this because we can see both these terms are equal. We'll cancel them off. 2 and 2 gets cancelled. 5 plus 3 is equal to 8 divided by 2 is 4. So I have sine 4x in the numerator divided by cos 4x in the denominator, and that is nothing but tan 4x. That is my RHS. That is my answer as well. So I have proved this. Correct. Moving on. Any point in the video, if you feel like you want to take notes, you can just pause it there, and whatever is written on the screen, you can jot it down in your notebook as well if you want. Move on to the next question. The next question is again of the same format. It's question number 18 that we're going to solve now. Sine x minus sine y divided by cos x minus or plus, sorry, cos y, it's nothing but tan x minus y by 2. Correct. So this is something that you have to prove. You're just going to do what we have been doing since the past 3-4 questions. We're just going to apply the entities and we'll be able to get the results, right? So let us try and solve LHS. So sine x minus sine y is nothing but 2 times cos x plus y by 2 sine x minus y by 2. Correct. And what is cos x plus cos y? Cos x plus cos y is nothing but cos x plus y by 2 cos x minus y by 2, correct? 2 and 2 gets cancelled. Cos x plus y by 2 gets cancelled. Sin x minus y by 2 upon cos x minus y by 2 is nothing but tan x minus y by 2, correct? And that is nothing but equal to our RHS. That is the answer, right? So that is done. We are going to move on to the 19th problem, right? Same format, but you're going to solve it as well. Prove that sin x plus sin 3x upon cos x cos 3x is equal to tan 2x, correct? Now, to solve this question, we're just going to do what you have been doing. We're going to expand the LHS. Sin x plus sin y is nothing but 2 times sin x plus y by 2 cos 3x x by, correct? And at the end, we have cos x plus cos y is nothing but 2 times cos x plus y by 2 cos, correct? This term and this term are similar, so they are the same, so they get cancelled. 2 and 2 gets cancelled, and what we are left with is x plus 3x is equal to 4x divided by 2 is 2x. So sin 2x divided by cos 2x, and that is nothing but tan 2x, correct? So that was our 19th question as well. We are now going to solve our 20th question, right? Let's try and do this. Question number 20th, correct? We need to prove that sin x minus sin 3x sin square x as cos square x. So there is a problem here, right? We are subtracting sin 3x from sin x, and in the denominator as well, we know that cos square x minus sin square x is nothing but cos 2x. So we have a problem of the inversion of sign on both the numerator and denominator. So to express that, can we write this as minus 1 into sin 3x? I am writing the LHS here. To prove this is equal to 2 sin x, sorry, I have to put it here. And this as cos square x minus sin square x. Can I do this? This is going to save me a lot of time, right? This and this gets cancelled. What I'm left with is sin 3x minus sin x upon, I know that cos square x minus sin square x is nothing but cos 2x, right? So I'm just going to directly put it here, cos 2x, correct? Now I'm going to expand sin x minus sin y. What is sin x minus sin y? Sin x minus sin y is nothing but 2 times cos x plus y by 2 sin x minus y by 2. And what I have here is cos 3x plus x by 2 sin 3x minus x by 2 upon cos 2x, right? 3x plus x by 2 is nothing but cos 2x. So this and this gets cancelled. What I'm left with is 2 times sin 3x minus x is 2x divided by 2 is x. So I'll get sin x, correct? That is my final answer as well, because that is the RHS term. So it is solved. In the 21st part, we are asked to prove cos 4x plus cos 3x plus cos 2x upon sin 4x plus sin 3x sin 2x, and we are told that this is equal to cot 3x. Let us try and prove this. If we can get this, it would be wonderful. So the term right here is 3x, right? and we have 4x and 2x. Whenever you see questions of this accord, try and find a common term. Because we want to make it into cot 3x, taking cos 3x as common and sin 3x as common in the numerator and denominator respectively would be helpful to us, right? That is something that you would have to see. So let us try and apply the identity of cos x plus cos y and sin x plus sin y with these four particular terms. Let us try and see what we get. So cos x plus cos y is nothing but 2 times cos x plus y by 2 cos x minus y by 2. So that is what I'm going to write. 4 plus 2 is equal to 6 divided by 2 is equal to 3. So 2 times cos 3x into cos 4 minus 2 is 2 divided by 2 is 1. So cos x plus cos 3x upon 2. 4 plus sin x plus sin y is nothing but 2 times sin x plus y by 2 cos x minus y by 2. So this term would become sin 3x as 4x plus 2x is equal to 6x divided by 2 is 3x, and this term right here would be cos x, correct? And we have sin 3x here as well. Can you see a pattern here? We'll be able to separate out 2 cos x plus 1 from the numerator and denominator. We can cancel that out and we'll be able to get the answer. Take cos 3x common in the numerator and sin 3x common in the denominator. So what you get is cos 3x 2 times cos x plus 1 sin 3x 2 times cos x plus 1, correct? This term and this term gets cancelled. What I'm left with is cot 3x, which is the RHS as well. Right, so it's solved. Moving on to the next question, we're going to solve the 22nd one. Correct? Let's try and do that. Prove that question number 22. We need to prove that cot 2x minus cot 2x cot 3x cot 3x cot x equals to 1. Correct? This is something that you're going to have to prove here. So whenever you encounter questions of these type, it is not feasible for us to start from LHS and reach RHS, right? We need to find a relation right here. Whenever you see questions of this type, understand that we need to apply the identity of cot here, right? In this question, first of all, that is something that you need to understand, because we are given the format like cot x, cot 2x and cot 3x. It is very easy for us to see that x plus 2x is equal to 3x, right? So first write that x plus 2x equals to 3x. And now to get this equation, apply cot on both sides. So on the, I'll switch it up here. Cot 3x you will have on the LHS. The RHS you will have cot x plus 2x. Correct? Now here you need to know the formula for cot x plus y. So I'll write it here for you. Cot x plus y is nothing but cot x cot y minus 1 upon cot x plus cot y. Correct? So you'll apply the same formula here and let's see what we get then. I have cot 3x as cot x cot 2x minus 1 upon cot x cot 2x plus cot x. Correct? Now we'll multiply the denominator to the RHS and let's see what we get. We get cot 2x cot 3x plus cot x cot 3x equals to cot x cot 2x minus 1. bring the 1 over to that side and bring these two terms onto this side, right? So transpose 1 there and these two terms here. What you'll ultimately get is cot x cot 2x minus cot 2x cot 3x minus cot x cot 3x equals to 1. Correct? Did you get how we get here? We push 1 over to that side, so 1 becomes positive and these two terms become negative, right? You can see their signs here. This term is right here. This term is right here. This term is positive, right? So we got what we wanted to prove and this question is done. In the 23rd question, we have to prove tan 4x equals to 4 tan x 1 minus tan square x 1 minus 6 tan square x plus tan 4 to the power tan to the power 4x, right? So to prove this question is going to be a lot of grunt work. So try and be with me when I try and solve this question. It is nothing but we have to apply the identity of tan x plus y. We know the formula of tan x plus y, right? Tan x plus y is nothing but tan x plus tan y upon 1 minus tan x tan y, right? So it is going to be a lot of work, but you're going to get there, right? Let's try and get from LHS to RHS. Let's see how that goes, right? I'm going to rub this off because we need a lot of space for this. I'm going to write tan 4x is nothing but tan 2x plus tan 2x plus 2x. Correct. And now we can expand this, right? We can write this as x plus tan 2x on 1 minus tan square 2x. Correct. Does that make sense? I'll simplify it a bit more. Correct. Now, again, apply the formula. Like if we do tan x plus x, we get 2 times tan x upon 1 minus tan square x. Correct. So we'll apply this formula into this equation again and we'll see what we get, right? We'll replace tan 2x by the formula we discussed. So we get, right, this is what we get, correct? Now we're going to try and solve this. So this becomes 4 tan x on 1 minus tan square x upon, so I'm going to multiply this right here and I'm going to expand this as well. I'm going to expand 1 minus tan square x. So 1 minus tan square x will be nothing but tan to the power 4 x plus 1 minus 2 tan square x minus, and this 2 right here will also get multiplied and this will become minus 4 tan square x and we have 1 minus square x ka whole square. Correct? Does it make any sense? It is going to take a while for you to get this. So if at this point you want to pause this video and try and figure out how we got from here to here, you can do that. But I've done nothing. I've just expanded this term 1 minus tan square x up above in the numerator, and I've just done that. I've expanded things, right? So I'll carry on from here to here. Carrying on from here, I get 4 tan x into 1 minus tan square x upon this term and this term gets cancelled by 1, right? And in the denominator I have tan to the power 4x plus 1 minus 6 tan square x, and this is ultimately the RHS. Correct. So it was a long question. We had to substitute the value of, we had to use the entity twice of tan x plus y, but we ultimately did that and we have reached it the answer. Correct. So moving on. In the 24th question, we have to prove that cos 4x equals to 1 minus 8 sine square x cos square x. And the way that we're going to do this is we are going to start from the LHS and we are going to go towards the RHS. Correct. So let us try and do that. So LHS. So cos 4x can be written as 1 minus 2 times sine square 2x. Does that make any sense? Let's try and do this. I'll try and make you understand more. Cos square 2x. This is very basic, right? I can write cos 4x as cos 2x plus 2x. Now expand, you get cos square 2x minus sine square 2x. Correct. In this, substitute cos square 2x as 1 minus sine square 2x here as well, right? Solve this, you get 1 minus 2 sine square 2x. Now we know that sine 2x is nothing but 2 times sine x cos x, correct? So that is what we are going to do. We are going to substitute the values. We'll get 1 minus 2 to the bracket 2 sine x cos x, and that is nothing but the whole square. That is nothing but 1 minus 8 sine square x cos square x. Correct. And that is nothing but our RHS. So this is the question solved. Move on to the 25th question. Okay. In this question, we have to prove that cos 6x equals to 32 cos power x minus 48 or plus 18 cos square x minus 1. Correct. So this is something that we have to prove. Again, the way that you're going to approach this question is you're going to break it down. We are going to break 6x into parts of 3x, and we have an identity for cos 3x, right? We have already found that out. So that is how we're going to solve this. Let us try. Start from the RHS, LHS. Let us see how we work our way in. So cos 6x can be written as 1 or 2 times cos to the power 2 3x minus 1. Does it make sense? Yeah. And cos cube x is nothing but cos 3x is nothing but 4 cos cube x minus 3 cos x. Correct. Now this is the expansion for cos 3x. If you are not sure how we got here, I'll do it just once for you, but you need to memorize this formula as well, right? Cos 3x can be written as cos 2x plus x, correct? And that is nothing but cos 2x cos x minus sine 2x sine x, right? And now into this equation, if you plug in the values of cos 2x here, and when you plug in the values of sine as well here, you're going to get this format, right? Does that make sense? Yeah. So when you do that, you're going to get this, correct? So just try and figure it out by yourself. You're going to get it and try and do that, right? So this is the formula that you should remember right here. minus 1. So this is this. And when you open this up, you get the term inside, you get this x, and this becomes minus 24 cos to the power 4x plus 9 cos square x minus, correct? This becomes 32 cos power 6x, sorry, 6 here, minus 48 cos to the power 4x plus 18 cos square x minus 1. And this is nothing but the term on our RHS, correct? So we've solved question exercise number 3.3 and we've taken up a good 1.5 hours here. The exercise that remains in this chapter is the miscellaneous one, and let's see how many questions we have. So we have a good 10 questions in the exercise 3.4 as well. So what we're going to do is we're going to tackle the exercise the next time, and we're going to see it, right? So this is all for today. Thank you.